this week, next week, and the week after. And then you are off for 2 weeks. Then you're back for 2 weeks. And then you're off for a week.
Okay.
I know, it's a really weird one. It's because we started so late, and yeah, it's all odd. Okay, so that's the recording started eventually. So good morning again. No code today. Just before we started recording, I was talking about the assessment. And of course, one of the things that we're going to get you to do in the assessment isn't just to produce code. It's going to be creating plans. Plans for the code, plans to test, plans for handling, all that kind of stuff. Oh, it was Maureen that started the recording. Thank you. Thomas, it's not recording 31 minutes. It means that the meeting's been going for 31 minutes and 56 seconds, but the recording can start at any point. I don't know why Maureen gets to press the button and I don't. I wonder if this means that the lecture belongs to Maureen now.
I never started it, I joined, so it's no me. I just pressed the button.
Yeah, I might be emailing you later if I need access to the recording. We'll see what happens. So, yeah, so today is...
Shit. I didn't realise that. Do you want me to stop it and then you can start again?
No, just leave it going, just leave it going. The worst that can happen is you give me access and I can grab it, it's fine. But I might see it because it's our meeting that I've set up. Teams changes on a weekly basis. But yeah, we can just have the Maureen channel from now on, you're right. It's far more fun. Okay, so the stuff today is about all that. It's about planning and testing and how to make a code that's more robust. So some of the stuff we've looked at before, but I want you to take notice of it because the plan at the moment is that the assessment will be given out, but the submissions will be in two parts. In that we're going to get you to submit the plan, including the test plan. And we're going to do that before we get you to move on to create the code. And if you don't submit the plan and the test plan and all that kind of stuff, you won't be able to do the code. Because despite what we say, there's a whole bunch of people still want to rush into just typing up stuff. And you've seen that even when I'm doing it, that it's not a valid way to go because you end up spending more time trying to fix the code that you type in than you actually do solving the problem. So the planning is vital. So that's what today is going to be about. So there's some code samples in it, but not many, and I'm not going to do any of the coding that's in there. Stop it. I passed on your comments about Teams last week, and I don't yet know what Jerry's planning in terms of it being a team project. As soon as I know, you'll know. Okay, so the first thing we want to talk about is planning. And we have looked a wee bit at this before because the first thing we want to look at is something called stepwise refinement. And we looked at it, but I think it was back in T1. And so we'll just go over it again just in case it slipped your mind. The idea is that if you have a big problem, it's hard to solve. You can't just solve a big problem at once. It's a lot easier to break it down into a lot of smaller problems and then solve each of those individually. The fancy name for that in programming is called
यार भैया इन्ने पैसे उधर चल गए, इन्ने घरे पाए सी, इन्ने पिंड पाए सी, इन्ने बैंक पाया उधर ही.
And that's me told Raoul. So this is called top-down design with stepwise refinement. The idea is you write down what the problem is, and then you figure out what problem that big problem is made up of. So all the smaller problems. And then the smaller problems can also be split up, and so on until you have small enough problems that are trivial to code. You know that they're trivial to code because what you're aiming for is a plan that you could take and give to someone else, and I highly recommend that you try this. When you're creating your plans, team up with someone informally and swap your designs and see if the person that you've swapped with can understand your design and could code the program from it. If they can, you've designed it properly, and if you can't, you haven't.
If they can't, they just can't program.
No. But what they could do is they could program it in anything they wanted. So the other thing about the plan is that it is platform and code neutral. So we've been doing Python, but this plan could be implemented using C, Java, COBOL if you want. The point is, any competent programmer could take your plan and implement it. It's not like making a tutorial for the next programmer, it's like making a detailed plan for them, Roland. And in fact, in real life, this tends to be what happens. The person that creates... Pardon?
So it's like a blueprint.
Yeah, a blueprint. And in real life, you tend to split up those tasks. So the person that creates the plan is different to the person who implements it, is also different to the person who tests it. We keep all those things separated out if we have a larger team. So this, I think, is the same example we used in T1. You remember way back, I got you to create a program that took a whole bunch of marks and gave you back an average.
If I remember correctly, that was the first program you asked us to write.
So that was the big problem. The big problem is get a bunch of marks and calculate the average. So you can start to think about what the different parts to that are. So there's clearly an input part. There's clearly an output part. There's going to be a calculate part in between. And there's going to be some other stuff that you're going to need to have to record some information. So things like an average. So we can start to think about this problem and start to split it up into those different component parts. So the first one is thinking about what information we're going to have to store. The list of the marks, the average, whatever it's going to have to be. Getting them, so inputting the marks. And here we've just got one step for both calculating and outputting. That might be one step, it might be two, depending on how you set it up. Each of those becomes easier to see. Now that you've been programming for a while, I imagine that if I gave you two numbers and asked you to calculate an average and output it, that's a trivial task for you now. And that's what we're trying to get to, a trivial task. On the other hand, number two, inputting all the marks until we're done, that's slightly less trivial, and we might want to think about how we're going to do that. Here, I slightly disagree with how Jerry has planned this out. Because what he's done is he's decided that what we're going to do is repeat until there's a trigger value. So he's already decided how you're going to implement this. We're looking for a mark of -1 or something. I don't think I would make my plan like this. I would just say get marks until finished, and then decide later on what finished actually means. So regardless of that, the steps are reasonable. Prompt for the test score, get the test score. Add the test score to a running total, and add 1 so you know how many inputs you've had. So again, as we break these down, these become trivial. You know, add 1 to a number of scores. It also means that we can go back to our step 1. So we've remembered that we need to declare and initialize the variables. And as we go through it, we can say, okay, well, one of those variables is going to be a running total. So we probably want a variable for that. And we probably want to set it to 0 to begin with. Same with the number of scores. So as we start to break it down, we can look for the kind of data that we want to save and add that to our list and set up initial values. Like this. Because Jerry has gone a wee bit further and decided that the repeat's going to be until a trigger value, and I think what we've done in T1 was something like repeat until the input is -1 or something like that. He's also set up a variable for trigger value. So that's 2, which actually feeds back into 1, and then we can go into 3, which just splits up nice and easily as calculate average using those 2 variables that we've set up, and then outputting the average. And the point with both 1, 2, and 3 is that hopefully every one of you can now look at that plan and see in your mind's eye some code that would make that work. Everyone happy with that so far?
Yeah, as far as I can be.
The other thing, of course, is that's all language independent. I could implement that in Pascal. I could implement it in C. Actually, I probably couldn't because I've never liked C and I'm not very good at it. But you get the point. We can implement what we've done in any language because our plan is just about solving the problem. Roland's question there is actually a really salient one. Is there a limit to how much detail we give? And the answer is no. And it's partly about experience. It's about knowing where your plan will translate to trivial pieces of code. Which is why the people that do the plans tend to be people that can program. You wouldn't just give it to somebody who's never done this before. And actually, a career progression tends to be programmer to systems analyst, and it's the systems analyst who creates these kinds of plans for the programmers to do. So you will create it knowing in your mind's eye what a trivial piece of code should be. So that's the detail, Roland, and it's about knowing what's going to be required by the programmers. So the analyst isn't just an analyst, it's an analyst who knows how to program. The other nice thing about planning, and we've got a very trivial example here, but there's nothing to say that we couldn't take our plan and give part 2 here to one programmer and give part 3 to another programmer and then bring them all together at the end. Because we've split up our task, we can also split up our manpower and split up our programmers. So as you get bigger problems, you know, you're watching this on Teams. It wasn't created by one person. You're watching a PowerPoint presentation. It wasn't created by one person. It was designed and then it was split up and a whole bunch of people programmed it and it was all brought together. So having that plan means that you can start to see how the big solution can be split up into smaller tasks that can then be assigned to different people. That makes sense?
Yeah.
So whenever you're given a problem, that's how you should approach it. You should think about it in terms of the problem and think about it in terms of how you split it up. And even if you are the programmer and the analyst and the tester, you should still do that. Maureen's saying that if you work for the Secret Services, you'll never know the full program. Actually, that happens quite a lot. I mean, you have an idea what you're working on, but there's no real need for you to understand what other people are going to do. Think of it like these modules that we've been importing. You've been importing random for a while. The person that created that not only didn't know what program you were going to create, they didn't know you were going to use it or where you would be in the world. What they've done is create some code that you can access. All
AAA game studios, like that's just a norm there. Depending on what department you work in, you pretty much have no idea what the end game was even going to look like.
And of course, that actually really helps, because if you're talking about games, what you might have is one team who do, for example, the display engine, which is really handy because that display engine, just like our random module, can then be reused again and again for multiple games. I'm trying to, what is it, the Unreal Engine is used in dozens and dozens of games.
There's Unreal, and then you have Unity, there's CryEngine, there's a lot of, like, everyone has their own proprietary engine.
Because it's one piece of work that can then be reused. And the fact that they've split it out as a separate problem means that it can be reused again and again. And again, even if you're using this for yourself, you can see how that applies to initially when we're defining functions, now when we're doing classes with methods, how you could take a particular part and just say, okay, well, we'll take this and we'll make a black box. We'll make a black box that takes an unknown number of numbers and returns a list of those numbers and how many there are and the total. That's the sort of thing that can be used again and again. And if you create that well enough, you can just go and grab it and bring it in again and again. And that's exactly how coding works. You've been importing modules that other people have used, like random. But there's nothing to stop you importing your own modules. So you might go and create a whole bunch of modules for things like that, for getting input, for checking input, for doing whatever. You can create your own set of modules and then reuse them again and again, just like the game studios do with their display engines. So this is how people work, and there's a reason for it. It works well. It means you can split up code. It means you can test it separately and be happy that it works. And then you can reuse it again and again. Because testing is key. You know that. I mean, we test things all the time when we've been doing them. It might be informal. The test might be hit the play button and see if it works. But it's still testing. Of course, we're going to move on from that. We're going to do a more methodical testing plan. That will be part of your assessment, and it will be part of the marking scheme for your assessment. So it's not just about hitting the button and hoping for the best. It's deciding what the program has to do, thinking about the type of inputs it might take, coming up with a plan to test all of those inputs, and then see what's going to happen. So again, we'll go back to a bit of code that we did in T1. You'll remember that we extended the marks and we got it to return a grade. And we had limits for where those grades were. So if your mark was between 0 and 39, it was a fail, 40 to 49 is a C, and so on. Remember doing that one?
Yep.
Okay. So if this is our problem, what we want to think about is how we are going to test this. Now, I want to stress this. You think about testing it before you've written a single line of code. There's no point in writing the code and then thinking, well, I wonder what the best way to approach this is. The grade program does seem so easy now, Roland, you're right. And Maureen, you're right, we're just about to talk about boundaries. One of the key things is deciding how you're going to test it. It keeps you honest. I've mentioned this before, but when you create your own software, you don't want it to fail. It's natural to say, well, I've created this, I want it to work. And your natural instinct is to want it to work. Of course it is. Why would you create something that you were wanting to break? It's part of the reason why testing is separated out in bigger companies. You give it to somebody who isn't emotionally invested in having created the code. So one way to do that when you're working on your own is to create this testing plan beforehand. Decide what your program has to do, decide how that can be properly tested, and create that before the code gets anywhere. So here's an example of the test plan for the grades. If you look online, there's a whole bunch of oh gosh, what's the word I'm looking for? Templates. There's a whole bunch of templates for setting up testing plans. But it all looks similar to this. You've got a number in the left-hand column. Which test is it? Test data, or your input. What is it you're going to test? A quick description of what that does and what you expect to get out. What we want to think about is all the different parts of the program that we should be testing. So here you can see we've tested 44 and 56 because they're smack bang in the middle of our C's, B2s, and so on. We also spoke about this before, something called an equivalence class. In other words, if you get a mark of 0, it's equivalent in grade terms to getting a mark of 39. That mark of 39 is not equivalent to getting a mark of 40. So we have to look at the boundaries between those equivalence classes. The boundaries where one answer clocks over into another, and you can see that there. We've got 49 and 50, the highest value for a C and the lowest value for a B2. So we end up in our test plan testing the boundaries of each output, the lowest and the highest for each output, and a sample somewhere in the middle. And that's a reasonable start to creating a test plan. We okay with that so far?
Yes.
Okay, the next columns in our test plan here are the actual result and the action. Here for the B2s, the result, we expected a B2, it displayed B2. So we are happy, we don't need any action. We did have a problem, however, with our C's. We wanted a C and it displayed a fail. So our action is going away and checking our code for those boundary numbers. Roland, very good question, and I'm going to come on to that later in the lecture. The question is about non-expected values, and I'm absolutely going to talk about that quite soon. Here's my next issue with these slides. Jerry said that we are going to create a retest. So he's marked them 30, 31 and 32 to retest what were 6, 7 and 8. I don't agree. Anyone care to speculate why?
Sorry, repeat what you were just saying there, because I've just kind of lost myself in that.
When he says retest, does he mean he's going to run the whole test and you think he should only run the test for that section?
I think he means it the other way around.
Other way around. So the next slide says, so he's got a retest here that says, 30, 30, 31. So he's created extra plans, 30, 30 and 30, 31, 32 to do these same ones again. I am not a fan because
In case your changes affect the rest of the program?
right. So if we're doing something that's going to check the boundaries of a C, which of course is right up against a B2, isn't it entirely possible that in fixing the C, we break the B2?
Yeah.
So
in the end, you have to just run through the whole test again.
You have to run through the whole tests again. That can be a problem where you have a massive program, which is again part of the reason why we split it up. Previously in functions, now with methods. What we can do is if we have a class that's encapsulated, what we can do is we can write a test plan for that class. And then once we are sure that the class works okay, then we can ignore that. We can say, yes, that's been done. So even if we're changing something else in the rest of the program, we don't have to go back and test the class again because we're happy that that works. The one in the slides, on the other hand, Jerry's saying, well, we don't have to test B2 because it works. I'm saying, no, we absolutely do have to test B2 because in fixing C, we could have changed the value and got the B2 one wrong. Exactly. If we modify anything, we have to redo anything that could have been affected. So if we have things properly encapsulated into a class and that can't change, then we don't have to retest them. But if it's one big program, then yes, we do have to retest them. "15 is composition and 16 is encapsulation." Sorry, Sargon, can you give me an example? I'm not sure what that question's asking. I'll go on with the lecture, and if you come up with an example, put it back into the chat. Okay, so do you see where I'm coming from? It's not just about, oh yes, this worked once, therefore it will continue to work. Even if it worked once, if you then go and change the code, you might break it. In fact, chances are we will break it. So we have to go through and check it all again, which is again one of the reasons why we want to encapsulate things and have them tested. Because when we're testing our program, we've imported random, we don't start to think, well, is the random stuff working okay? It's its own module, it's been tested, we're happy with it. It's another reason why in larger companies, a lot of this stuff isn't done manually anymore. You'll set up these tests and you'll have automatic testing systems, and Python has them. You can go and look them up after the lecture. What you do is you set up exactly as you do here. You set up test cases, you say what the output should be, and then you can run those automatically. And as Pablo's pointed out in the chat, that means that you can run them once a day. And commonly for big systems, what will happen is you will work on the code. So say, you know, because all programmers work 9 to 5 and never any other hours. But commonly you'll check out the code in the morning at 9 o'clock, you'll work on your bit, you'll check it back in at 5 o'clock, and then the automatic testing systems will check the code overnight, and you'll come back in the morning to a list of errors that's been found in your code. You check it out again and keep working. Because as you can imagine, the more complex the program, the more complex the testing, and the longer that takes. Happy with that? Okay, as I've said before, testing is core to what we do. That's part of the reason it's in the assessment. We make you test. And as I said before, quite often we send it out to people who weren't involved in the program so that they can approach it dispassionately. So we start to see a bit more of a plan to creating software. It's absolutely not sitting down and opening up our IDE and starting typing. We start off with the planning. We then create a test plan. And only once we're happy with those do we ever start typing in a line of code. Now, once we've finished our code, we can come back and we can run through our tests and our test log. Stage 2 and stage 3 are iterative. So if we find issues with the testing, we go back and we change the program and so on and so on. And in fact, it could iterate all the way back to step 1, because we might find that our plan was wrong. We were going to approach a problem in one particular way and it doesn't work. Sometimes you have to revisit that. Don't be shy about it. You won't get things right first time all the time. So if you have to go back and look at it and think, well, maybe I could have approached this in a different way, that's absolutely fine. But initially, when you start, get yourself a pad or a whiteboard or whatever you work best. But I would keep away from a computer. Find yourself a comfy chair and start writing. Start imagining the problem in your head. It's part of the reason we did some of the exercises where we presented you some code and we said, what will the output be? It's starting to think about this abstract thing about how problems work, because what we're doing with any program is solving a problem. And if we want to solve a problem, we need to think about what the problem is and how we would solve it manually first before we can automate it. If you can't imagine how you would solve the problem just by telling someone how to do it, then there's no way that you can solve the problem by telling a computer how to do it. So you have to think about it and design the solution, and then you have to work through it yourself. If you've created this if you've created this stepwise top-down refinement, top-down planning stepwise refinement plan, if you get to this point, you can actually run that through in your head. You can say, okay, well, in my head or on my bit of paper, prompt for and accept a test score. So in my head, I'll do 40, 50 and 60. I'll add the input score to the running total. So 40 plus 50 plus 60 is 150. Add 1 to the number of scores. I've got 3. That's fine. So my output should be the average. 150 divided by 3 is 50, and that's what should be output. And you should be able to work that through in your head. You should be able to do it by hand, so that when you get to the point of creating the test plan, you know what the answer should be. How are you going to create a test plan if you don't know what you're expecting to come out? So you have to understand the problem, you have to understand the data, and you have to understand what you're going to do with them to get your output. So design your solution first. And while you're doing the solution, think about how you're going to test that solution. And only once you've done that, once you've created the solution, once you've created a comprehensive test plan for everything you can possibly think of, that's when you can start creating code. And even then, you might want to take the plan and start thinking about pseudocode. Would the testing include mistakes that are not from the code but from a logical error? So that's what I'm saying about understanding the solution as well. So you're saying, well, if we used the wrong equation. Well, if you've used the wrong equation, then you haven't understood the problem. If you're trying to work out the area of a circle and you're not using the equation pi r squared, then you haven't understood the problem. And that's the other thing that we programmers have to do. We have to understand problems in all sorts of areas. Because, as you well know, there are software solutions in all sorts of area, from maths, science, commerce, whatever. And to actually create the solution, you have to understand the problem. If you have used the equation 2 pi r to create a bit of software that calculates the area of a circle, then you haven't understood the problem. And you're right, your code could work, but the fact that the solution on paper wasn't correct in the first place will mean that you have an issue. Which comes back to what I'm saying about testing it on paper first. If you know that the area of a circle with radius 1 is 3.14, then you can check that you've used the right equation. And if instead of using pi r squared, you've used 2 pi r, which gives you 6.28, you know that you've got it wrong. So the plan for the assessment at the moment is you will submit your plan and your test beforehand. So we want them first. That's the plan just now. I assume it will stay that way. Does that make sense, Roland? Happy with that?
It makes sense, but I'm not happy with it.
It's just a declaration of the obvious. You cannot program a solution to a problem that you do not understand. You have to understand the problem. Full stop. Of course you do. It would be like having a navigator in the car and saying, drive me to Edinburgh, and the navigator going, what's an Edinburgh? It would make no sense whatsoever. So
Sorry, we don't serve food here.
Yeah. Okay, so you can then start to create the code, and when you've created the code, you can then test it. And as I said, it's an iterative process. If you have problems in step 3, if you have problems in the testing part, go back to the code and fix it. If what you're doing is actually trying to fix an incorrect design, then you might need to go all the way back to step 1 and redesign. But if you're redesigning, make sure you check your test plan to check that your test plan is going to be correct for the new design as well. Okay, that's that bit. Everyone happy? And have we got any questions? Okay, I'll take silence as no. And what I'm going to do now is
happy little campers.
Go back and address the question Roland asked half an hour ago. Because what we said was, you know, you're entering 40. Have you got the right output? Yes. But what happens if you enter X? Let's look at error handling. And again, we've done a wee bit of this before, so some of it should be a recap of things that we've looked at before and have implemented before. But I want to give a few different ones because they're going to be key to you creating a robust program for your assessment. And one of the things I would suggest you do, so I've been talking about creating functions and methods. When we go through these, think to yourself how you can create some self-contained code that would implement these solutions that I'm going to show you, so that you can reuse them again and again. So that, for example, if you have to get an integer, which is a fairly common issue, maybe you should be creating a function or a method that gets an integer and puts in all the error handling you can think of. And then every time you go to get an integer, you just reuse that piece of code. You don't ever want to repeat yourself. Okay, so let's look at some different types of errors that we can get and how we might handle them. And we'll start with the integer one. What happens if? So again, you've seen this before. A program that's very happy if you give it a couple of numbers, but very unhappy if you suddenly put in something that isn't a number. So here, we've entered the first integer correctly, but we've entered a letter for the second one. Oops. And it's given us an error. Now, sometimes these errors are really helpful. No, actually, always these errors are really helpful. But what can be tricky is understanding them. So as you get more experience, you start to understand them better. So what we're going to do is just have a look at them and try and translate some of them to give you a better idea of what they're saying and what you need to do about it. So it starts off here with value error. We've got an error with the value, okay? Invalid, I understand that. Literal just means the input itself. It's not a variable, it's an actual value. So it's an invalid literal. So in this case, it means the k. It means that the k is invalid. For int, okay, well that makes sense. K is not an integer. And it even tells you what base you're working in. We're not working in binary or hexadecimal, we're working in base 10. So it's telling you we've got a value error because the input, the literal input that you have for that integer is invalid because it was looking for a base 10 number and what you've entered is K. Remembering, of course, if it was base 16, A through F would be quite happy. If we know that this is a value error, we can do something about it. And again, we've looked at this before. We can try to catch an error. And we've got some code that lets us do that. Remember, when you're doing this, encapsulate it. Put it in a function or put it in a method, but make sure that you set it up once. So here, for example, is a function that checks for a value error. All it's doing is having a parameter passed to it, which we hope is a number. And we're going to check that. Hopefully, you're looking at that code and can understand what it is. Anybody get any questions about that code?
I like the try expect. That's how you filter for errors, right? For these unexpected values.
Yep. So we set up a Boolean saying that it's not valid. So we assume that it's not valid to begin with, so that we will go into this while loop at least once. So we start off invalid, which means that it will go into the loop. And we're going to try something. What we're going to try is say number becomes int num. So we are casting it as an integer. And then we set valid int as true. If that caused an error, so if it caused what in programming is called an exception, something that went wrong. So we're trying this. If it throws an exception, and that exception is this value error, then we can say, nope, sorry, it's not a whole number. Try again. And we get the new input. And we go through the while loop again. And it keeps doing that until we actually have a number. So they can type in anything they want, but you can't move on until you actually get an integer. And it would work something else. Sorry?
If we put a float instead of integer, when we casting it, we don't change the type, so the answer will be correct instead of wrong.
What you probably want is another function that does a similar thing, but casts it as a float instead of an integer. And depending what type of input you want, you would call the different functions. So you might have a function that checks for an integer, a function that checks for a float, a function that checks for a Boolean, a function that checks for text. So you could have a function that checks for anything according to the rules that you have set. Okay. And of course, you could extend that out. You don't just have to check for value errors. You could say, give me a number in the range 10 to 20. And you could also extend out that function to say, check for value error in range. You can set it up to be whatever you want, depending on what you wanted to do.
Okay, thank you.
So this particular one, Ansumana, is only for value errors at the moment. So we can run it. And instead of just getting a standard input, we can check for a value error. And again, I would probably change this code. So here we've got an input. We've asked for an input separately. Why wouldn't we put that into the function as well? Why wouldn't we just get the input? And if we were worried about what our prompt was, we could pass the prompt as a parameter as well. Regardless of that, the point of this one was a value error. So here we can see we've entered 5, then we've entered t, and our function said it's not a whole number. We've tried with 7.8. We can't cast 7.8, which is a float, to an integer, so it's not a whole number, and it says try again until we get our second whole number and it works. Everyone happy with that and how we check for a value error before we move on to the next one?
Yep, I'm good with that.
Okay. So a value error is the wrong value of a specific data type. So it would be the same thing if you tried to get a float. It would still raise a value error if you didn't type in a float. There's a whole bunch of different errors that you can check for. So remember the code said exception on value error. There's a whole pile of those things that you can check for. Arithmetic, attributes, floating points, index, type, division by 0. There's actually more. These are just the common ones. So you make an arithmetic error if you try to multiply 5 by x. You might get an index error where you try to access a list member that doesn't exist. Division by 0 when you try and divide by 0. So knowing that these errors exist and knowing that you can check for them means that you can set up your program to do that in the beginning. So let's have a couple of them. We'll look at division by 0 to begin with. So as you know, if you try and divide anything by 0, it's impossible. Arithmetically, it's impossible. So here where we have a quick program to divide things, if we divide by 0, it comes up with our 0 division error. Okay, this one that we pointed out there. So what we're going to do? Well, we'll do the same thing that we did for checking for integers, but in this case, we'll do it for division by 0. Same idea, we pass a couple of numbers, we divide them, and if we get a division by 0 error, we don't ask again in this case, we don't ask for another number, we're just saying, no, not possible, you can't divide by 0. So you can do whatever you want, depending on what your program should be doing. It's not just always about going and getting the next one, saying it's wrong. Sometimes they might be the numbers. And you're just reminding people those aren't reasonable values. You could create one function that will check for multiple errors. You're quite right. And in fact, that's exactly what you should be thinking about. Maybe for your function, you should be checking for lots of these things at once. Sorry, that was in response to a question in the chat from Ansamana. So yes, absolutely. You can expand these. So these are very simple checks. You could check for a whole bunch of things, depending again what was appropriate for your program. And if we do that, you can see here that we get the error message that it's not possible. We can do the same for other data types. So you'll remember that for lists we have indexes. So here we've got John, Paul, George and Ringo, and we're going to print out the the item corresponding to those indexes. I'm a bit confused though, because we'll get 4 items in the list and it's upset about when we try and print the 4th item.
Yeah,
Why does
you're asking it to get the 5th item like this because it's starting to count from 0 in terms of indices. Oh, you got a -1 everything.
Okay, so don't forget that lists start at 0. So Beatles 0 is John, Beatles 1 is Paul, Beatles 2 is George, 3 is Ringo, and Beatles 4 doesn't exist. But we do have an index error. So again, we can check for index errors. So instead of just going and getting the item out of the list, we can set up a function that checks the list and says, okay, does it exist? And if it doesn't, you can say, well, we don't have that one, sorry. We can check for other things like type errors. So here we've got a simple subtraction, but what we're trying to do is subtract a string from a number, which in this case gives a type error because you can't subtract a string from a number, not surprisingly. So we can create our same sort of thing. We can create a function for subtraction that checks for type errors as well and gives us an answer if it's a type error. And Answer Man is exactly right. Why don't we check for all of these things? Why don't we think of all the things that could go wrong and set up functions that will check for all of these at once? Even better, if there's something that we forget to check, then we can go back to our function and add it in. And all the other places where we go to get that input will automatically be upgraded to the thing that we've just realized we should have checked for in the first place. So by taking these things, putting them into a function, and then calling the function instead, we can make sure that our program is more robust, and it also helps us update whenever we have an issue. Everyone happy with that so far?
Yep.
Okay, nearly there now. Remember that these are the predictable errors. So it's things that we're thinking about that could go wrong, and we're saying, okay, well, if this goes wrong, here's what we want to do. So it's worth having a look at the error types that Python has and trying to think how you might implement them and whether they're useful in the program that you're creating. If they are, then you can use a try except to work with those, excuse me, and deal with them before they cause a problem further down the line. So Roland, I hope that answers the question that you had 3/4 of an hour ago. Anybody got any questions? What week can you get the slide? Again, sorry, I'm not sure what you're asking. These slides are on both Teams and Aula, and this is week 17, if that's what you mean. Is it not an Aula? Jerry told me it was an Aula. He's telling me fibs. Okay, you can get it on Teams. Okay, I'm assuming it will appear in Aula at some point, but as long as you can get it on Teams, it means you can get it anyway. Any other questions? No. Okay, your lab work and your submission for this week is to create the error handling examples. When you're doing it, please don't treat it as a typing exercise. Try and understand what's happening and try to think about how you might extend it, how you might check for more than one thing at a time, how you might, in other words, make it better. Jen, what pages are you missing? In the slides, you mean?
Yeah, when I downloaded it, it's corrupted, I think, obviously, because Teams had a senior moment. I've emailed Jerry and asked him to either pop it on Ola or email me a copy. I thought I was just missing one page, but when I get to the end, I'm missing about 10 pages. It's just blank.
Okay, well, if you have emailed them, that means I don't have to, so thank you for that. Okay, any other questions? It's all gone very quiet, which I assume means that there are no more questions. So what time is it? I make it 11:15, so make sure you take a break. We'll go into the lab as usual if you need a hand, but please take a break. It's not good for you to be sitting around just staring at a screen for all time. So I will certainly be taking a break, and I'll be in the lab about 1:30 or so. Okay, so I will stop recording. Or maybe Maureen's going to have to stop recording. I don't know.